Structure and interpretation of computer programs, bite size. 1.3.3 Procedures as General Methods. We introduced compound procedures in section 1.1.4 as a mechanism for abstracting patterns of numerical operations so as to make them independent of the particular numbers involved. With higher order procedures such as integral procedure in section 1.3.1, we began to see a more powerful kind of abstraction. Procedures used to express general methods of computation independent of the particular functions involved. In this section, we discuss two more elaborate examples: general methods for finding zeros and fixed points of functions, and show how these methods can be expressed directly as procedures. Finding roots of equations by the half-interval method. The half-interval method is a simple but powerful technique for finding roots of an equation f of x equals 0, where f is a continuous function. The idea is that, if we are given points a and b such that f of a is less than 0 and also less than b, then f must have at least one 0 between a and b. To locate a 0, let x be the average of a and b and compute f of x. If f of x is greater than 0, then it must have a 0 between x and a. If f of x is less than 0, then f must have a 0 between x and b. Continuing this way, we can identify smaller and smaller intervals on which f must have a 0. When we reach a point where the interval is small enough, the process stops. Since the interval of uncertainty is reduced by half at each step of the process, the number of steps required grows as theta of log of L divided by t, where L is the length of the original interval and t is the error tolerance, that is the size of the interval we will consider small enough. Here's a procedure that implements this strategy. Define the procedure search that takes inputs f, the negative point, and positive point. Let the value midpoint be the expression average applied to neg point and pos point. If close enough applied to the neg point and pos point returns true, return the midpoint. Let the test value be the expression f applied to midpoint. Check and see if positive applied to the test value is true, then apply search to f, neg point, and midpoint. If negative applied to the test value is true, search f, midpoint, and positive point. Otherwise, return the midpoint, or else return midpoint. We assume that we are initially given the function f together with points at which its values are negative and positive. We first compute the midpoint of two given points. Next, we see if the given interval is small enough, and if so, we simply return the midpoint as our answer. Otherwise, we compute a test value with the value of f at the midpoint. If the test value is positive, then we continue the process with a new interval running from the original negative point to the midpoint. If the test is negative, we continue with the interval from the midpoint to the positive point. Finally, there is the possibility that with the test value is 0, in which case the midpoint itself is the root which we are searching for. To test whether our endpoints are close enough, we can use the procedure similar to the one used in section 1.1.7 for computing square roots. So let's put this in first. Cool. Define the procedure close enough that takes inputs x and y to check and see if, to apply the less than procedure to, or to check to see if absolute value of x minus y is less than 0.001. Search is awkward to use directly because we can accidentally give it points at which f values do not have a required sign, in which case we get a wrong answer. Instead, we will use search via the following procedure, which checks to see which of the endpoints has a negative function value and which has a positive value, and calls the search procedure accordingly. If the function has the same sign on two given points, the half-interval method cannot be used, in which the case procedure signals an error. Define the procedure half-interval method that takes inputs f, a, and b. Let the value a value be the expression f of a, and let the expression b value be f of b, be the expression f of b. Check to see if the a value is negative and the b value is positive. And return, if it's true, return search applied to f, a, and b in that order. If not, check to see if the negative b value is true and the b value is negative and the a value is positive. If that's true, apply search to f, b, and a in that order. Otherwise, return the error, values are not of opposite sign, a and b. The following example uses the half-interval method. Did I put that in there? No, I didn't. To approximate pi as the root between 2 and 4 of the sine of x is equal to 0. Let's do half-interval method, sine 3.141111, whatever. Okay, here's another example using the half-interval method to search for the root of the equation x cubed minus 2x minus 3 equals 0 between 1 and 2. The half-interval method is with inputs the lambda of x, which is negative of x cubed times 2x, so minus x cubed, 2x, and 3. So apply that to all of them in that order, and input the values 1 and 2. Okay. Oh, I see what I did wrong. Put these ones in there as well. Oh. That's weird. Interesting. Okay, we'll just skip that and figure out what happened later. Finding fixed points of functions. A number x is called a fixed point of a function if x satisfies the equation f of x is equal to x. For some functions, we can locate a fixed point by beginning with the initial guess and applying f repeatedly. F of x is f of f of x, f of f of f of f of x, until the value does not change very much. So using this idea, we can devise a procedure fixed point that takes as its inputs a function and an initial guess and produces an approximation to a fixed point of the function. We apply the function repeatedly until we find two successive values whose difference is less than some prescribed tolerance. So, define the procedure tolerance that takes 0.000001 as input. Define the procedure fixed point that takes f and first guess as input, and define the procedure close enough that takes v1 and v2 as input, and close enough checks to see if the absolute value of v1 minus v2 is less than the tolerance. Define the procedure try that takes guess. Let the value next be the expression f of applied to guess. If close enough applied to guess and next is true, then return next. And apply try to next. If not, apply try to first guess. Oh wait, no, if close enough applied to guess and next are both true, then try next. I'm not sure what that is actually. For example, if we can use this method to approximate the fixed point for a cosine function starting with 1 as an initial approximation. So let's put this in. Okay. Oh, I see what I did wrong. Hold on. Let's try this. Alright. Let's see if this is going to work, because I can't really tell what's going on. Okay. Similarly, we can find a solution to the equation y equals sine of y plus cosine of y. So y, apply fixed point to the procedure that takes input y, that adds the sine of y and cosine of y, and sine of y, cosine of y, and then fixed point, the other input is 1. So we have this whole thing as one input, this procedure is an input, and then 1 is the next input. Okay. Oops. Okay. 1.25, which is what we got. The fixed point process is reminiscent of the process we used for finding square roots in section 1.1.7. Both are based on the idea of repeatedly improving a guess until the result satisfies some criterion. In fact, we can readily formulate the square root computation as a fixed point search. Computing the square root of some number x requires finding a y such that y squared is equal to x. Putting this equation into the equivalent form y equals x divided by y, we recognize that we are looking for the fixed point of the function y as it approaches x divided by y. Therefore, we can try to compute square roots as define the square root of x to be the fixed point applied to the procedure that takes with input y, that is x divided by y with the fixed point x divided by y is the first term and 1 is the second point term. So 1.25, and that is the same thing. Interesting. Unfortunately, this fixed point does not converge. Consider an initial guess y1. The next guess is y2, x divided by 1, and the next guess is y3, blah, blah, blah. This results in an infinite loop in which two guesses, y1 and y2, will be over and over oscillating about the answer. One way to control such oscillations is to prevent the guesses from changing so much. Since the answer is always between our guess and y and x and y, we can make a new guess that is not as far from y of x and y by averaging y with x and y, so that the next guess after y is 1/2 of y plus x divided by y instead of x divided by y. The process of making such a sequence of guesses is simply the process of looking for the fixed point of y as it approaches 1/2 x times y plus x divided by y. So divide square root of x, fixed point to be the fixed point applied procedure lambda of y that is the applied to the average of y divided by x, average of y and x divided by y, and fixed point also the last input is 1. Note that y equals 1/2 times y plus x divided by y is a simple transformation of the equation y equals x divided by y. To derive it, add y to both sides of the equation and divide by 2. With this modification, the square root procedure works. In fact, if we unravel the definitions, we can see that the sequence of approximations to the square root generated here is precisely the same as the one generated by original square root procedure of section 1.1.7. This approach of averaging successive approximations to a solution, a success we call average damping, often aids the convergence of fixed